morning. I'm happy I have Brad Carr here finally. He's a professor, associate professor at the University of Wyoming. He's our speaker today, and he's a polymath. He started his PhD working in data from the Carr borehole, the deepest borehole in the world, I guess. He was doing some of the BSP processing of that. Then I think he moved to Saskatoon. Did with Zoli Hanyang. Then Oak Ridge Labs. Then he went to the industry for 10, 13 years. And then he went back to the academy at the University of Wyoming. And I guess he's now in charge of the instrument center for high resolution for the whole US, right? And we are fortunate to have him here today. And I think he's going to talk about some of the stuff he's doing in Old Facebook. So I hope you enjoyed the talk. I don't think the microphone is working.
Yeah, it is.
Oh, it is?
Okay.
Okay.
No, you can.
Well, no, I've got this. So
You got yours.
yeah,
Okay.
I think I'm good. Well, thanks, Ramon. Thank you all for having me here. This is a great honor. Today, we're going to talk about part of the research that I've been doing over the last 10 or so years at Wyoming. All of the research that I'm involved with currently, despite my background in reflection seismology, has really turned into what I like to call near-surface geophysics. So I'll use any of the geophysical techniques that are appropriate for the depth of interest. Today, we're going to talk about geysers, hydrothermal geysers in Yellowstone National Park. And we'll focus on that today, but basically you'll find that I'm using every applicable geophysical technique to help us define the various parts of the structure, the dynamics, the water flow, you name it. There's probably a geophysical method that we can apply that actually gives us some insight, and the more methods we apply, the more insights we get. So, yeah. Yeah, well, we'll use that. I'll quickly acknowledge this is not just me, obviously. As all geophysics goes, it's a team. And there's various people, as well as the US National Park Service, that allows this research to happen. I point out one of my master's students, Daniel Srella, who's currently finishing a PhD at the University of Iceland. So that is not Yellowstone behind Daniel there. That's the volcano south of Reykjavik that he got himself in front of at this point. But Yellowstone is a great scientific environment, especially if you're interested in geyser systems or hydrothermal systems, because it basically has the largest concentration of hot springs on the planet. There's over 10,000 features between the geysers, the hot springs, the pools, the mud pots that exist. There's a diverse fluid chemistry in each of these things. What you're seeing on the right there is Old Faithful, so the very iconic geyser within Yellowstone. There's a mixture of gases, mantle origin, crustal origin, and meteoric sources that all mix to basically affect things. And then if you just get into the life part of Yellowstone, you'll find that there's all kinds of, I like to call them Archean protozoic bacterias that exist in these hot thermal features. Okay, so these are not necessarily the same bacteria and biota that we exist with today, but a whole mix of ones that survive only in 80, 90 degrees C water. So that's a little rare. Anyway, there's many things, obviously, to study there, but the question really in today's talk is, what does the structure look like, fundamentally? If you go to Yellowstone today, you'll see this picture, this map, this cartoon, and it'll describe the various features, meaning the hot springs, the geysers, the two kinds of geysers, the cone geyser, as a faithful fountain geyser, which we'll talk about is what I'll refer to as spouter here in a second. But if we're looking here, this is a very simplistic view of the water system that's feeding the very near surface. If we were putting a depth scale to this, it's probably, for the geyser systems, it's only 60 to 100 meter, maybe 200 meter. So this is a good cartoon for the visitors to the park, but it's not really a realistic view of what the pipes look like, the infrastructure sort of looks like underground. So we have to do a little bit more work to follow up on that. And today what we're going to talk about is why these Yellowstone geysers actually fit into the greater hydrothermal system, how they work fundamentally. We like to call them a bubble trap, and I'll explain that in a minute. Previous efforts on geyser structure and what we know, there's really not much, believe it or not. There's geysers all over the planet, but the amount of effort put into studying them structurally and dynamically is low. And then what we might expect in the Old Faithful area, that there's very fundamentally, I think, two kinds of geyser system genesis. And we'll talk about that in a second. Then we'll look in detail at Spouter Geyser, which is a pool geyser. It's about 1 kilometer or so away from Old Faithful, and then Old Faithful itself, which is a cone geyser. And then we'll look at the dynamics, or how we can geophysically map dynamics of these geysers. So it's a lot of what we would like to call time lapse, right? Time lapse recording of various kinds. So let's back up. We'll go to the big picture of water in a place like Yellowstone or any volcanic system. Could look at Etna, could look at Tenerife, you could look in the Canaries. A lot of things are similar. You're basically having surface recharge, whether it's snow or rain, primarily getting to depths that get close enough to the magma system to have those waters be reheated. And instead of running on being driven by gravity systems, they're driven then on a temperature system, which means they want to go back up to the surface to equilibrate. Okay, so big picture water cycling is very similar to this. The very near surface is where we get this, what we call a phase separation between a vapor phase and a fluid phase. Usually one is slightly acidic, pH of 3. This vapor phase is slightly acidic. The fluid phase is more neutral at about a pH 7. If we focus in on the near surface hydrothermal systems in this figure here, this cartoon, you can see a little bit more detail with the acid system, or the vapor phase. Basically, the vapor phase of the slightly acidic system creates the mud pots. The pictures that you see of a nice clear blue pool is not an acid system. A nice blue clear pool at Yellowstone is basically one of these neutral chloride systems, right? And basically it's a pH of 7. The silica comes out of solution as the temperature decreases in the fluid, so that these things actually armor themselves. So they basically make their own pipe. This guy, the acid system or the vapor phase system, is actively weathering the surrounding rock or glacial till or whatever that happens to be the host material. So very cloudy, muddy pots here, very clear blue, usually hot water over here. Now, how do we take that further a little bit? If you're looking at volcanic systems, you generally like to break the world into sulfate content and chloride content. Meteoric systems, surface water, rainwater, snowmelt, tends to fall down in the low chloride, low sulfate realm. As you get more acidic or higher sulfate in a volcanic system, you're going to plot up here, where you have meteoric mixing with gas. essentially. But as you trend down either this line or this line, you're going more towards a hydrothermal state. So waters that are coming from deeper than and having very little surface influence. If we look at most of the features around Yellowstone, they kind of plat on this sort of mixing line where you're trending towards a hydrothermal system. As you get to Spouter and Old Faithful, they're actually pretty close to a pure hydrothermal system. So again, think about when these things are erupting, you're not really erupting an acid system. You're erupting a neutral chloride water. It's hot, generally around 80 degrees C. But usually, actually, by the time Old Faithful rains down on you, it's only about 40, so it doesn't feel that bad. But I wouldn't stick my hand in the actual fluid in the thing. But anyway, you've got some meteoric mixing, but not a whole lot. You're almost purely at a hydrothermal system. This other star here is a very classic feature. It's called Beryl Springs, that basically is trending hydrothermal water purely. But you can see most of these dots represent features in the park. So most of the features in the park are slightly acidic, right? They're mostly mud pots. They're very cloudy kind of things. But there's only a few bit of these sort of really neutral chloride systems, and very few that trend towards a total meteoric source. So we're living in this world of almost pure hydrothermal input. Now, how do geyser models work? We're kind of going through some background here. So I talked about the bubble trap system. Bubble trap system fundamentally means there's a reservoir. I like to call it the geyser reservoir. It's a place where fluid and gases mix. When the gas pushes enough of the fluid down to the level of escape in this feature that's commonly known as the gun barrel. In this case, this was a schematic from a Russian work that was done in the 60s or something like that on Kamchatka. This is another data set that was looking at microseismic bursts at Yellowstone at Old Faithful, actually. And so we were just looking at the bubble burst going on and kind of using that to say where the structures were and how they behaved. But basically, again, you have a reservoir. There's fluids that are coming up from the bottom. This is sort of a model version of that, where you have air or gases displacing the water to a point where they can escape and push any water that was in the gun barrel system out. That pushing out of the water is what the geyser actually is, right? So when this geyser reservoir has enough gas displacing the fluids to the point of the egress, then any water trapped in here is what gets forced out. All right. Then once it's forced out, there's probably the fluid essentially fills up most of the reservoir again, right? And the gas then has to start percolating back into the reservoir, pushing it down again. If it works cyclically, as it does in Old Faithful and Spouter, then there's some period of time. At Old Faithful, it's about 90 minutes before it runs and erupts again. At Spouter, the other one we studied, it goes about an hour and a half. So, and they do actually working on a periodicity geyser is actually really nice because when you're recharging and when you're erupting. So it gives you the ability to define those time windows very well. But this is the fundamental model. So again, if you hear me say something about the bubble trap or the geyser system, the geyser reservoir, this is what I want you to think about this, right? A volume, mostly with fluid, being displaced by a gas, CO2, steam, it doesn't matter exactly what, SO4, could be any of those, and basically pushing the water level down to a point where it has to depressurize, forcing water out of the gun barrel. All right, we're not quite there yet. We haven't gotten to the fun part yet. We're still understanding how these systems kind of act and behave. There were boreholes drilled in Yellowstone National Park in 1970 by the USGS. if you tried to do it today, there's no way the park would ever let you do it. But at that time, they drilled some boreholes, and this one, Y1, was drilled next to that spouter geyser that we'll look at. All right. And if you look at that, this should seem kind of normal, right? This is depth here down to about 60 meters. And we know the bedrock here is rhyolite. And we encounter that at about 65, 62 meters. But above there, we've got all these nice rock definitions, right? So conglomerate, sandstone, sandstone. The very top is what we call sinter. It's a silica deposit, right? It comes out of that hot water cooling that I mentioned. So everything, when you look at these features, has this white material on the top. That's referred to as sinter. It's just basically silica, okay? But I want you to first note that they're giving rock designations here, but we know that there is only rock starting right here. So what is actually here? So technically, this is glacial till from the surface all the way down to 62 meters. This is unconsolidated glacial till. This is not a rock deposit. The geology that was attributed to the borehole, though, looks very rock-like. That's because silica sinter acts like glue. It consolidates that material. And if you think about it, the geyser structure that I'm talking about has to be built within glacial till, right? We're trying to make a solid feature in stuff that isn't hard rock, all right? So keep that in mind. I mean, we're going to assume that the sinter is being deposited from the water path from the rhyolite all the way up to the surface. Okay, I'm going to show you an analog of what I like to think about when I talk about how these structures got built. We flew airborne data in 2016, electromagnetic and magnetic airborne data over the whole active part of the park. This resistivity profile here is based on those data. So it looks like, you know, the resistivity is going down as you go to the rock. That's a little backwards if you know electrics, but we'll talk about why that's an odd thing. I think we don't really want to focus too much on it as much as we want to focus on the temperature curve, right? If we look at when the borehole was drilled, they were taking temperature measurements down the hole. And you can see that pretty quickly, it goes from, you know, 60 C at the surface. I would say it's more like 80 C. I've measured it at the surface and it's more like 80, but whatever. We're quickly within that glacial till zone getting down to 170 C before we even hit the rock. So there's a high temperature gradient here, right? And remember that hydrothermal water as it's coming up is depositing silica the whole time, all right? So we're building the structure, and what does this structure potentially look like? I like to say a really good analog to the geyser structures that are getting created in glacial tills would be very much like basically an oceanic hotspot. This is Hawaii, right? So if you imagine in Hawaii, those magmas are coming up from the seafloor and accumulating and accumulating and accumulating over time and eventually reaching a point where they get above the surface of the water. Effectively, if you took away the water here and you just called all the blue glacial till and you called the hydrothermal input of water that's depositing silica as it's trying to equilibrate to the surface, it's a rather similar analog, all right? Now, the other interesting thing about this, and a hotspot analogy, so to speak, with the geyser structure reservoir anomaly, so to speak, is that silica sinter also keeps the hydrothermal waters from mixing with the meteoric or the surface waters in the glacial till, right? If it did, there wouldn't be a pressure problem that would cause the geyser, right? We need to have that structure be isolated from all of the regular water that's surrounding it. That would cool it down. It would probably depressurize the reservoir. It wouldn't erupt. Okay, so we're looking at two systems, a surface water system and a hydrothermal system, and they're kept from interacting very well with each other by that silica sinter wall. That's critical. Otherwise, a geyser isn't going to happen. All right, so let's go into the details now. Finally, the fun part. So this is called Upper Geyser Basin in Yellowstone. The Old Faithful is right here. You can see all the buildings and the infrastructure. It's rather large right here. This is the park, has a lot, the park buildings, park administration. Close by, about, well, maybe 2 kilometers away, is Spouter Geyser. It's a different type of geyser. It's a fountain pool type, which means it doesn't have a cone. It basically looks like a pot on the surface, and eventually that pot fills with water and then boils over. And it throws water maybe 10 meters, 20 meters max into the air. Not like Old Faithful. Old Faithful throws water, it's more like 40 meters. It's not the tallest geyser in the world. The tallest geyser in the world is also in Yellowstone. It's called Steamboat. It throws water about, let's see, 300 feet. I got to do that translation real quick. That's about 90 meters, I think. So this is not Old Faithful, although very majestic and very periodicity, very, 90 minutes, everybody can see it. It's not the biggest geyser on the planet. That's actually about 30 kilometers away, just to the north. But we'll look at these two because again, they are very convenient because their periodicity, like this one, Spouter Geyser, it's a pool geyser. So during its normal existence, it's either full of water and pushing water 10 or so meters, maybe max, and then it drains. Looks almost like a toilet bowl, actually, right? So it's got its water here. When it's erupting, it's, a lot of steam coming off. You'll notice that we are allowed to do our research in the winter here when there's no tourists. Otherwise, they would never let us in. So that's why you'll see a lot of snow in these pictures. Good thing is you never have to worry about where you walk because if there's any threat, there's no snow. So that it's warm. So in this winter when we were working, there was about 2 meters of snow right here, and you knew where not to go, basically. But these are the two states. This is the eruption state. This is the recharging state for Spouter. The geophysics we ran here, quite extensive, various kinds. Basically, there's 2 geysers of note here, Spouter, which is over here, and another one called Whistle right here, and another one called Cliff Geyser over here. But we were really focused on Spouter since it's the most predictable. We ran electric resistivity tomography lines, DC resistivity lines along this profile, and this profile. We also did refraction seismic on those 3. And we also did GPR, and then these bigger black lines represent NMR, surface NMR that we recorded here. I probably won't spend much time talking about details on the methods. If you're not as familiar with some of them, please, ask me later. Nuclear magnetic resonance. So of all the geophysical methods we have, most of them are proxies for a physical characteristic. If it's seismic, we're looking at velocity density of a material, say. If it's NMR actually is where we take the magnetic dipole of water and we knock it out of its preferred spin axis by a magnetic pulse, essentially. And while that thing processes back to its Earth state, which is the Earth field, we can record some voltages with that. So it's the only geophysical method that detects water directly. So it's kind of strong for that. Really good to use here because we're looking at how water goes into the geyser system, and then as it changes, we want to see that fluctuation. And so nuclear magnetic resonance is also done a lot in boreholes. It's really either surface or borehole work. And always we're looking for water content or porosity directly, how much water is actually there. So here again, imagine we're looking at times when we want to know how much water is in the structure versus not in the structure. That's why we use it. What's that? Here we don't have a borehole that we could access, but we had to run at surface NMR. My preference is always I like borehole NMR a lot better, honestly, but you know, the park doesn't have boreholes that they would let us go into. In fact, they didn't even know where the borehole was here. It was buried. We had to find it for them with magnetics because they had a casing still there. So anyway, these are the methods we use primarily. We're just going to look at a few of those. So this is the refraction data, the seismic data. The reason we wanted to look at these is we assume that the silica sinter cement that creates the reservoir structure is going to be denser than the surrounding glacial till. So we would expect the seismic velocities to be higher. And if you look, right, a little bit underneath there, unfortunately, you can see that the elevated velocity information underneath both of those two, underneath this guy, maybe not, it's harder to see on this, but certainly Whistle here. Everywhere we have a geyser of mapped surface presence, we have an elevated velocity profile. So that fits our hypothesis that the structure is denser, therefore a slightly higher velocity. The other thing we assume is that the structure itself is going to be resistive electrically, right? Because again, the silica structure is not going to be allowing sort of electric current to move quite as easily through the system as compared to the glacial tills that surround it. So if we look at those data, we can see again that our hypothesis is fairly accurate in that the higher resistivities nicely correspond to where we have the feature. So in this case, this is what we want. This lower one is just a difference change between the eruption to recharge, because we'll look at that a little bit more in detail later when we talk about geyser dynamics. But certainly we would expect the structure to have a different resistivity when it's full of water versus primarily full of gas, right? Gas is a very good resistor electrically. So we were looking at the dynamics. In fact, we produced 2 papers out of this work. One that was just looking at structure because we felt that nobody had really done it. And secondly, we wanted to look at the dynamics and how geophysics could be used in the dynamics. So this lower one is really just that, working on that dynamic thing. So remember now, we've got things that are higher seismic velocity and higher electrical resistivity. We need to find, at Spouter, we need to find the gun barrel, right? A gun barrel on a pool geyser is difficult to find because you just have a pool on the surface, right? If you look at Old Faithful, there's a big cone. It's about 10 meters high, right? It's pretty easy to say that's where it's coming out. Not so much here. At Spouter, the pool is right here. And this is electrical resistivity imaging. You can see nicely where the gun barrel leaves the geyser structure right here, comes up this thing. It's actually offset. We didn't expect this. It was actually offset a little bit more to the, I guess that's the southeast than we had originally anticipated, but it's still interesting to see. These features still exist, even for the pool geysers, essentially. So that was another real useful thing to learn. This again was a 3D actual acquisition of ERT, not just 2D profiles. So I mean, it would be nice if we could have done a larger scale and looked a little deeper with it, but there was some other challenges logistically for that. But this in itself was useful, and knowing what that structure looked like allowed us to create effectively a cartoon of the geyser structure at Spouter. Basically where we have this anthill-like structure. So as hydrothermal fluids of high temperature, high silica move their way into the surrounding glacial till, they basically get deposited as they cool, the silica does, but there's still permeability pathways for the hydrothermal water, and eventually it'll work its way up to the top, work its way through the Spouter, the gun barrel type structure, to the pool itself. Now, we're not talking about the dynamics yet, so I'm not introducing the eruption zone. We'll see in a minute here when I get to the dynamics that about at this level in the geyser structure is where all the magic happens, so to speak, where the pressure change in the gases that are coming in with the fluids actually cause this to push water out. But this was just the structure, so we just want to look at this. We know we have fluids coming up through the rhyolite, basically hot water fluids, hydrothermal in origin, creating this structure with deposition of the silica. Now, I would argue, and then we haven't really proved this, but the formation of where the gun barrel starts to happen is usually about where the static water table is, okay? If you think about it, diffusion, all of this is under the water table, all right? So hot water is displacing cold water to create this structure. It's a very simple diffusion problem, if we think about it physically. But when we get to the surface, when we get to the water table, we don't have good diffusion going on anymore. We have very focused sort of diffusion at that point because the hydrothermal waters are trying to direct path to the surface, okay? And so we can pretty much say a lot about the gun barrel and how they work, whether it's a cone geyser or a pool geyser, just based on where the water table is. So even though these systems are generally running off a temperature problem, and they're trying to get cooler, trying to get lower pressure, they don't behave unlike normal waters in certain ways. And the diffusion problem is one of those ways. All right, so takeaways from spouter. This is spouter going off. It fills up and then just, erupts for a while, well, an hour and a half or so. Seismic velocity is higher in the hydrothermal reservoir structure compared to the surrounding glacial tills. That seems pretty obvious, but I'll show you an example of why that wasn't so obvious previously. The resistivity, the electrical resistivity, is higher in the hydrothermal reservoir structure compared to the surrounding glacial tills. Now, even though this structure has water in it, which you think would lower the resistivity, the predominant amount of the material in the geyser reservoir structure is silica. Therefore, it's going to be a higher resistivity electrically in bulk. All right. The bubble trap is offset. We learned when we did this, the bubble trap is offset to the east-northeast of the spouter pool by about 10 to 15 meters. So even though it's probably right about where we're standing as we look at it. We're looking to the northwest here. So that hill that you can kind of see over there is the caldera rim of the Yellowstone volcano. But yeah, this is what, this is winter again, so it looks like more steam than anything else. But this is a pool geyser. This is spouter. I actually like it. It's kind of a good geyser. It behaves really nicely. If we look at Old Faithful, on the other hand, very cone geyserish, obviously, right? This whole thing is the sinter cone at the surface. This is Old Faithful going off. This is Old Faithful kind of before it goes off. This is a transient electromagnetic system that we have that we were running around various places, looking at how deep the rhyolite was relative. We could have a whole nother talk. I could give that to you now if you wanted, about why geysers form where they form. I have some pretty, I think, well-supported understanding and hypothesis about that. This is our EM MAG airborne survey that we flew in 2016. You'll see where this is going on in a second. There's Old Faithful. So if we look at the data from this line, this is what we see. Generally, we get anywhere from 200 to 400 meter depth penetration. Hot colors here are resistors. Blue colors are more electrically conductive. Old Faithful sits here in the middle. Obviously, there's a lot of hydrothermal inputs, probably a lot of clays also to lower the resistivity. But we do have some interesting areas that are probably off to the side. This is the caldera edge. You can see another area over here where we have low resistivities that are probably following lava or rhyolite boundaries, actually. So there's usually areas between the major tough flows where you have sort of higher water infiltration and water movement, not just associated with the hydrothermal system, which is what's down here. But we could, you know, that's great if you're looking at big picture. For the big picture things, I refer you to Carol Finn's paper from about a year ago that talked about most of the airborne work. But we're going to go back now to the details of Old Faithful itself, because we really, you know, we didn't see a whole lot of, if we look at this, you might say, well, where's Old Faithful, right? It's somewhere in here. It's right in the middle, actually, but can't really tell a whole lot more than that. So let's get in detail. So some seismic work that went on, actually it was some folks that seismicity work, the micro bubble bursts that I showed you earlier for that was done by Jean van de Meulenbroek up in Paris, or I think he's Grenoble, I'm not sure. Anyway, he's French. And this was done by the University of Utah. So they basically put broadbands around a whole bunch of the area, under the boardwalk, et cetera, all around here. And with that, they came up with what they thought was going on with the geyser structure. And they kind of made this circular blob here, a little bit offset from Old Faithful. So using Jean van de Meulenbroek's work, and then they just sort of added to it. But they called it a low seismic velocity. And that kind of makes sense because it's probably a water-filled structure, but does it really? Now, we've already shown that these geyser reservoir structures are strong relatively. They have higher seismic velocity and they're higher resistance. So this was at odds a little bit with what we were seeing. And so I decided we should go in and test all this. They were not, this was basically seismic tomography, so not exactly imaging. Therefore, you know, we can give them a little bit of credit that, you know, velocity control, you know, is a little bit hard with what they were doing. So they just drew a circle and said, this is where the structure needs to be. So I used that and modified where I put all my stuff. This line right here was electrical resistivity and seismic refraction again, but meant to go through the middle of their structure. Like if their structure existed, we should see it. Then I ran the park only let me run one hammer seismic line, you know, on this side of the cone. This is the cone. They didn't want me getting any closer. They were really not happy about us swinging a sledgehammer on Old Faithful. They were worried that we would damage it. But then they were okay with us putting ERT lines or resistivity lines on these profiles. So we were able to see a little bit more. We also did TEM in a lot of places to map the bedrock. And we also did NMR encompassing the cone of Old Faithful to basically see if we could, you know, see how much water was really being present. So let's start with the University of Utah's definition of the geyser structure. So this is the seismic refraction along line 1. If the cone would have been right about here, 120 meters to the northeast. Again, these velocities are not very high. Here's our numbers down here. So the greens are around 2,500 meters per second. We're not really seeing anything elevated in the glacial till. Therefore, if someone asks me, I think that's not where the glacial where the structure is. We can see the top of the rhyolite pretty easily as, you know, we go from 2,500 up to almost 4K when we get into the rhyolite. You'll know, I should note already, for those of you not in the near surface, like 4 kilometers per second is like the moho for us, generally. So just so you have a little bit of context. So no high seismic velocity. Let's look at the resistivity. Same thing. In fact, we see a decreased resistivity in any of the areas where they predicted that structure to be. Again, that would only make sense if the whole thing was completely saturated and not a silica sinter rich body. All right. So I would say we pretty much proved that their estimation of where the structure is not correct. So again, this model, not going to happen. So we started looking at our data, the ones that were going across the structure. This is one of the one seismic profile, right? And again, we're still north of the cone by 45 meters, but we still see elevated seismic velocities within the glacial till that correspond to where that thing is. So I think our hypothesis is still pretty accurate. Resistivity-wise, it's a little harder to see, but you can see that these are lighter colored, right? All the way up. In fact, there's what looks like branches of it. Again, hot colors are very high resistivities. We're looking at low, but again, these are saturated glacial tills out here. So they're going to be really low electrically. We're expecting that the structure itself and the gas in the structure are probably what's elevating these resistivities by about 10%. So if we look at what we think the structure sort of looks like, it would be this, essentially. Now, we might be not at the right perspective for the gun barrel. The DTW is right here, but you can see that things change drastically as you go up above the water table. So we have generalized diffusion of the silica sinter below. As we get closer to this, we almost get that narrowing gun barrel effect to the surface. There's a video you could watch. It was recorded by a fellow of Westfall who was at Caltech in 1991. It's on YouTube. So if you want to see, they actually were allowed to drop a camera down the cone at Old Faithful, and they basically got to the water table. So they got about 8 meters below surface before you could just see frothing and boiling, and it was just a mess. Wouldn't go any deeper. And obviously they pulled it out before it erupted because, I mean, when it erupts, there's enough force that it would have just blown that thing up, 30 meters into the air. So now, what you're looking at here in this summary kind of thing is the magnetics. And the circle there is the cone of Old Faithful. The little red, octagon or pentagon kind of thing is basically where I say the structure is, as opposed to where the Utahns said the structure was out here. I say it's right here. Basically, we're seeing that the reservoir structure extends to the northwest, parallel and on the flank of a magnetic high. So here's the magnetic high. This is the only bit I'll tell you right now about my hypothesis of why these things form where they form. Basically, if you look for the edges of magnetic highs, that seems to be where the rhyolite is producing hydrothermal waters. We can look at other data sets at other geysers and sort of start to feel like that's reasonable. So it's probably a function of competency of the rhyolite. If this rhyolite hasn't been impenetrated by hydrothermal waters, it's going to stay intact, and this magnetic signature is going to stay intact. If hydrothermal waters move through a rhyolite, it weathers it and lowers the magnetic susceptibility. So if we look on the edges of these highs, more often than not is where we find geysers. Whoops. Let me back up for a second. And lastly, that anthill-like structure is roughly 55 meters wide, 100 meters long from the top of the bedrock to the DTW. And we also indicate that we say there's 3 pipe-like structures from DTW to ground surface, only one of which reaches the surface, which is the vent cone. So these other little areas out here and out here basically are failed vents, failed gun barrels. They didn't make it all the way. And again, this is formed by silica sinter, which elevates the velocity and resistivity. Okay, so in the last little bit here, let's talk about dynamics. We'll go through this real quick. I could talk about it all day just in itself because it's really fascinating just to be able to take the pulse of a geyser, right? Essentially, that's what we're doing. If we're doing time-lapse efforts, we're seeing how the thing behaves. All right, so here's spouter again. I'm just going to fly through this. So we set up electrical resistivity on line 1, so right over spouter's reservoir structure. And basically, we've recorded all day long. And basically, each one is roughly around 45 minutes in duration. So we can't be instantaneous, but we're pretty close to it with ERT. We'll get even faster with electromagnetics, but nonetheless, this is what we're stuck with for imaging. Basically, right now in this picture, we're 50 minutes into the geyser, right? Water's at the surface and this day. And you can see that there's this lower or slightly elevated resistivity and a bunch of different little paths all the way down to, 60, 70 meters. So we're well within the rhyolite by the bottom of this image. But if we keep going every 45 minutes after that, we'll see things start to change. So now, this is the end of the geysering event. And you can notice that what was over here at the cone is now shifting a little bit. It's like shifted over here comparatively. So it went from here to here. All right, that's weird. If we keep going, you can see that, whoops, went too far. That basically we're seeing the geyser structure with different amounts of gas. That's the long and short. Okay, so let me just cycle through that one more time, just so you can get a feel for how excited we were really when we saw this. Because it's like, I have another thought that essentially gas is what's driving this system. So if we assume that the fluid into the geyser structure is fairly constant, the thing that's really driving when this thing triggers and geysers is the gas. So the CO2, the steam, maybe the SO4, probably more CO2 here, but anyway. No consistency, right? Changing gas structure moving through the system. So this is all the way to a new starting of geyser structure. And if we look at this and we compare this to that, they look about the same. This one was geysering. And then the very last one here was just about to start. And those two are the closest images to each other that we've got. So really cool. There's a lot of other things we can look at. Whoops, sorry, come back now. Hey, I'm hitting the arrow too much. Okay, here's where I wanted to be. All right, this is a lot going on, and this is kind of how we'll end, right? This is done with transient electromagnetics. Okay, so this square was put over Spouter Geyser. It's a 40-meter square, and we're just recording every 6 minutes constantly for an entire day. All right. Well, in fact, this top one we did for 24 hours. So we left it overnight. And this one we did for 44 hours because we thought this one turned out so well that we wanted to do again. So on this thing, the colors represent the resistivity. So you can see it's very resistive at the surface due to the silica sinter in the first 5 meters and the rhyolite down at 60. All right. But everything in between is the variable resistivity of whether this thing's geysering or not. The black line represents a temperature curve. So we put a water temperature sensor in the outflow of the geyser. So every time spouter was going off and it was releasing water to the surface, we were measuring basically 80-degree water, well, 70-degree water, right? So when that stuff's coming out and hitting our sensor, it's about 70 degrees. And you can see there's these weird little pulses in it. That was really fascinating. So it's not a constant flow out, for one thing. But then when it would be done, when it was done geysering, the temperature sensor would basically fall back into air. And since this was in November, it basically dropped down to, between 10 and 20 degrees, essentially. All right. So you see these black line, right? And you see it go up, and then it goes down, it goes up, and it goes down. So this is us mapping the periodicity of Spouter Geyser. And not only that, but we're seeing it pulse at various times. And then we're seeing the resistivity shift. So if this thing decides to geyser for more than an hour and a half, as it did here and as it did here, we can see that the resistivity levels in the mid, like 20 to 30 meter zone actually are different. Again, we're looking at the dynamics of the system. We're looking at how the gas flux is changing. All right, I might have one more that we can look at, but real quick takeaways. Time-lapse DC resistivity observes these changes in the gas flux. That's really amazing. It'd be good if people did it all over on Etna, Chile, anywhere, Iceland, really, anywhere there's geysers. Time-lapse NMR highlights a difference. I didn't show you those data because I didn't really want to go into it a lot. But we basically, when this thing erupts, it erupts about 8 Olympic pools in an hour and a half. So imagine a 50-meter by 20-meter wide pool times 8. That's how much water this thing's getting rid of every time it erupts. The transient electromagnetics observes that upward movement of the water in the hydrothermal structure, which we see as sort of the change in resistivity of the TEM values, right? As it lowers, we're seeing water move up. As it increases the resistivity, that's more gas flux. Okay. I also would argue that we can see changes in the rhyolite, which is, I think, also due to the gas. But, you know, whoops, I went too far. One more, right, come back. The last slide. Oh, it just keeps going past. There we go. There we go. Okay, so we looked at part of this before, but now that we're talking about the dynamics, the only thing I want to add is the gas flux, right? So remember that 20 to 30 meter resistivity zone change we saw in the TEM data? That's basically right here, and we referred to that as the flash eruption zone. So that's that active part where fluid and gas interactions are going on. And you basically have to have, you know, prior to an eruption, you have to have enough gas pushing down on the fluids to force the water out the gun barrel. So this is where all the action is really happening. Underneath that, there's pretty much still fluids in the structure that are just sort of the reservoir, the water, hydrothermal water reservoir. But as soon as it erupts, that area is going to fill and basically then has to go through this whole process again of more gas input. At this particular place, it's really been monitored as CO2 being the principal gas that's moving into the spouter, but it could be anything. It could be steam also, it could be SO4. It doesn't really necessarily matter what the vapor phase is, as long as vapor phase is present. So again, this is the dynamic part of a geyser that, again, you should expect everywhere. Whether it's Iceland, whether it's, you know, Chile, who knows? It should all work this way. All right, and with that, I want to end. Take any questions that you have. This is a real common occurrence when you're trying to do geophysics. Yeah. Whoops, in Yellowstone. This I told Ramon, a mutual friend of ours was sitting in this chair. And he didn't see this bison come up behind him at all. And the whole time we're trying to say, you got to move. You don't want to stand there because they're really large. They're a lot larger than a cow. And when you're close to them, you don't want to be standing there. But anyway, we see them a lot when we do work. So.
Thank you very much, Brad. I guess you will entertain a question or two.